Hello and welcome to today's webinar, Advanced Analytics with Amazon Redshift and Amazon Machine Learning. Before we begin, let's walk through a few housekeeping items. On your screen, you can see a Q&A pod. Please submit your questions for our presenter and Q&A moderators at any time throughout today's presentation. We will address them anytime they submit and also as well as in the live Q&A session in the end. At the conclusion of today's presentation, there will be 3 poll questions proceeding live Q&A. Today's webinar is being recorded. We will send you a follow-up email with a URL to the recording once we verify the recording quality as well as a link to the presentation deck. And again, welcome to today's webinar, Advanced Analytics with Amazon Redshift and Amazon Machine Learning. Our presenters are Wagashi Dabo and Radhika Ravirala. Wagashi is a solutions architect at Amazon Web Services, where she helps customers architect and build out their applications on AWS. In a prior life, Wagashi worked on Booz Allen Hamilton, focusing on SOA and big data projects within the federal sector. Radhika Ravirala is a solutions architect also at AWS, where she helps AWS customers architect their big data and analytical applications in the AWS cloud. Prior to joining AWS, Radhika spent over 13 years gaining experience in crafting distributed applications at HP, Sun Microsystems, and IBM. Today with us, we also have Alex Ingerman, Senior Technical Product Manager for AWS Machine Learning Platform, and Greg Corella, Business Development Manager. Alex and Greg will engage with you and answer your questions throughout today's presentation while Wagashi and Radhika present. Now, Wagashi and Radhika, welcome, and I'll pass the floor to you.
Okay, thank you very much. Thank you again for taking time out of your busy schedules to attend this webinar on Advanced Analytics with Amazon Redshift and Amazon Machine Learning. In this webinar, we will start by looking at current trends in data-driven development. Then, look at how Redshift is evolving from a traditional data warehouse and expanding its capabilities to handle more sophisticated data analytics use cases. We will then discuss how to build advanced data-driven applications with Amazon Machine Learning, and then use Amazon QuickSight for visualization. Finally, Radhika will take over and do a brief demo, and then we will open up the session for Q&A. One of the most interesting trends in computing over the past several years is the way working with data and analytics for developers. All developers are doing something with data in addition to their web, mobile, or backend development efforts. Developers now treat instrumenting and collecting events as one of the most important parts of the development process. And because of this, applications are logging tremendous amounts of data, and so developers are picking up the skill to analyze this data, to derive some value from it, and to build useful applications on top of the data the application generates. Data-driven development falls under the following 3 categories. First is the retrospective data analysis, where data is collected, stored, and analyzed to answer very specific questions about what happened in the past. For example, instrumenting how long customers spent in your application. The second type of data-driven development is to capture the information as it comes in and use it to immediately take action. For example, building dashboards to capture the current state of the business. There's one more step beyond knowing what is happening here and now. We can use the data we already have to make accurate, actionable predictions about what will happen in the future. We can build a new breed of smart applications using these predictions. Machine learning is becoming an increasingly important tool to build advanced data-driven applications. So what is machine learning? Machine learning has many definitions out there, but you can think of machine learning as technology that automatically discovers patterns in data and then leverages those patterns to make predictions about future data. An example of a pattern is, if a product contains the keywords jeans or jacket, then the product very likely belongs to the apparel category. Machine learning systems learn from examples, and this is very similar to how children learn a language or learn to recognize objects. So there's a very simple equation here. Take your data, add machine learning technology, and smart applications become possible. So what does a smart application look like? One common example of a smart application is, based on what you know about a user, will they use your product? How long will they use the product? Will they upgrade out of the free tier? This is a good example of leveraging what you know about a user to make a prediction and then act on it. Another example is based on what you know about an order. Is this order fraudulent? Should it be flagged for manual review? Should you contact the customer and confirm the order? Or should you just go ahead and cancel it directly? So these are all choices that are available to you. Another example is based on what you know about a news article. What other articles are interesting to your audience or to a specific person? So the list of machine learning use cases is endless. There are a few other examples here, like personalization. And an example here is, say for example, you watch a Netflix movie. The next time you log back in, you find recommendations based on movies you've watched before. Targeted marketing is also very common, and this is where ads are placed in your browser based on your activity on the internet, and so on. So now that we've seen several examples of smart applications, here's an important question. Why aren't there more smart applications? So what our customers are telling us is that there are three primary barriers. Machine learning expertise is rare. Building and scaling machine learning technology is hard. And closing the gap between machine learning models and applications is time-consuming and expensive. Before we dive deeper into machine learning, let's take a step back and look at retrospective or historical analysis through data warehousing. We always like to start here. Redshift is a fast, fully managed, petabyte-scale data warehouse that makes it easy and cost-effective to analyze all your data using your existing business intelligence tools. For less than $1,000 per terabyte per year, you can focus on your analytics while Amazon Redshift manages the infrastructure for you. Here is a review of the Redshift architecture. Redshift is a columnar, multi-node, shared nothing cluster database service. It is a leader node that you connect with your SQL clients. Data resides in the compute nodes, and that's where all the work happens. All the work happens in parallel directly through the compute nodes. Since this is an advanced Redshift session, we will not focus on the details. This is a getting started guide for Redshift, and we will provide a link at the end of the webinar. Today, Redshift is successfully deployed for a variety of use cases. So our customers come from virtually every market vertical, running virtually all use cases. And they range from startups to large enterprises. For example, Nasdaq is using Redshift for its end-to-end encryption, which meets their compliance requirements. And they are able to achieve faster and richer analytics than their legacy warehouse. Amazon.com, our parent company, and NTT Docomo operate petabyte-scale Redshift clusters in production. Pinterest saw 50 to 100 times performance gains when they moved 300 terabytes from Hadoop to Redshift. Nokia saw 50% reduction in costs. So you can see for historical analysis, Redshift is a great platform for data warehousing workloads. So now let's look at how we're expanding Redshift's query capabilities to enable more statistical analysis. We've been iterating quickly and we add SQL functions regularly. This is because we want to expand the range of analytics you can do in SQL. We have added over 25 since launch, new aggregate and window functions, regex capabilities, and more. List arg, for example, is quite popular with our customers. The idea here is that you can aggregate multiple values into a single string, which is quite powerful. We also added the approximate count function, and so on. And we're going to continue iterating here, but we also want to enable you to add your own functionality to Redshift. And so for that reason, we've added scalar user-defined functions. UDF provide more flexible querying and analysis, enabling a broader range of analytic and data science use cases. You can write your custom functions in Python 2.7. The syntax is very similar to what you can do with PostgreSQL UDF. Because Redshift is a distributed system, you have to provide a keyword around whether your function is immutable, stable, or volatile, which is optional in Postgres, but required in Redshift. Redshift reserves the F_ prefix exclusively for UDFs to prevent naming conflicts. We do sandbox the UDFs, so you can't make file system or network calls. But otherwise, the full Python interpreter is available to you, and it runs as compiled bytecode in parallel on all the compute nodes. The Python library in Redshift comes with pandas, NumPy, SciPy for analytics. So those functions are available to you for use, but you can also bring in your own libraries. So here's one example. Say, for example, you need to extract the hostname from a URL or a referrer string from your web traffic. If you're using SQL, you could use a set of complicated regex expressions to extract your domain. Now, with UDF, you can just create a simple function, and in that function, you can import Python's URL parsing library to extract the hostname from the URL. You can use that function in your SQL query and pass in your URL. So you can see how UDFs give you an elegant way to expand the capability of your database and bring it into your SQL queries. So here's a more complex example. And we have a big data blog that goes into more detail about how you can go ahead and implement this Z-test UDF. And you can still create your own custom libraries. For example, if you have a complex scoring model that you've created outside the database, you can package it as a Python library, load the library into Redshift, and use it to score your data very fast. Our partners like Periscope have created UDFs that you might find useful for your workload. Some of these UDFs are for date manipulation, others are for JSON manipulation, and more. And I highly recommend that you take a look at them. And the cool thing is that you can start using them directly in your application today. Looker is also another partner, and they have created a how-to guide for UDFs. So as you can see, there are limitless applications for UDFs. We would love to hear about your UDFs, and it is possible we could bake them into Redshift. And if you'd like to share your UDFs with other customers, by all means, let us know. Now that we've seen how Python UDFs can let you perform statistics in the database, now let's see how you can connect R to Redshift to add predictive modeling. After SQL, R is the most commonly used programming language by data scientists. R provides a rich software environment for data manipulation, exploration, including graphical display. R is easily extended using packages. For example, Shiny Server is a visualization R package that allows you to create interactive dashboards. So in R, you can install the R JDBC package to load Redshift JDBC driver and then send SQL queries to Amazon Redshift. The difference here between Python UDF and R in this specific scenario is that you have to take data out of the database to do your analysis. You can also write R code directly using the dplyr package to analyze your data in Redshift. But first, you have to create a connection to Redshift using the R PostgreSQL package. Once you get a reference to your data set, you can analyze your data and visualize your analysis. And again, we also have another big data blog that shows you how to do this in detail. And you can do more with R. So once you have a reference to your data in Redshift, you can use a number of R packages to do predictive modeling, like in this example. So now that we've seen how Redshift is evolving to handle more sophisticated data science use cases, let's dive deeper into how you can build smart applications with Amazon Machine Learning. So what is Amazon Machine Learning Service? Amazon Machine Learning Service is a service that makes it easy for developers of all skill levels to use machine learning technology. It is not built for machine learning experts, but we find that machine learning experts also use and like the service. Amazon Machine Learning is based on the same robust machine learning technology that is already used within Amazon's internal systems that generates tens of billions of predictions weekly. One important feature of the service is that it easily connects and integrates with the data that you already store in the cloud in data stores like Redshift. The whole idea is that it removes the barrier of just connecting the dots from the data store to the machine learning technology to do predictions. Amazon Machine Learning is built to eliminate the gap between having models and using those models to build smart applications. Production deployment only takes a few clicks. Ease of use is incredibly important to us. What we have found is that building machine learning models really has two stages. The first stage is experimentation. And this is where you're trying out different data sources, different ways to transform the data, different ways to use machine learning technology to approach a problem. And in this stage, it is really helpful to work with interactive tools that let you do many experiments easily. The second stage is putting the models into production. This involves automating model training, deployment, and use. For example, tying the actual prediction generation activities with your application's business logic. So once you have your models and they are ready to go into production, you have a full API available to deploy these models and to query them for predictions and to train and evaluate new models as new data comes in. So the Amazon Machine Learning API support is available in all our major SDKs. Prediction querying capability is also bundled in the AWS mobile SDKs. And this makes it really easy for you to create mobile applications that use predictions. So let's talk about the technology. So Amazon Machine Learning comes with smart data transformations. When you enter your data into Amazon Machine Learning, it is analyzed and data transformations are suggested automatically based on the data content. There's some intelligence built into the system to specify which transformations apply to which variables or input attributes. You can take the suggestions directly, or you can edit and modify as needed. And then from a data store integration perspective, again, we wanted to eliminate the gap between data and models by making Amazon Machine Learning connect directly to the data that's already stored on the AWS cloud. When using the Amazon Machine Learning Console or API, for example, you can connect to Redshift to execute a SQL query and grab the results, and you will see this in the demo. So once you have a model and you're ready to generate predictions, the Amazon Machine Learning Service provides a fully managed end-to-end service for prediction generation, either in batches or in real time. There's no need for you to provision any hardware, and there's no need for you to know ahead of time how many predictions you will need. We handle all that for you. So now let's talk about building smart applications. When building a model with Amazon Machine Learning, there are 3 stages to take into consideration. Build and train the machine learning model, then evaluate and optimize the model, and the final stage is to use the actual model to retrieve predictions. During the first stage, we first create a data source object that connects to your data and computes summary statistics on it, and then it surfaces up really cool interactive data exploration experience so that you can inspect your data. Once you confirm your assumptions, you're then ready to transform and train your model. During the second stage, that's when you evaluate the model to understand the model quality and how it maps to your business objectives. As you'll see in the demo, the service contains a rich interface to allow you to accomplish this goal of basically understanding the model and then fine-tuning it to align with your business goals. So the final stage is to use the actual model to retrieve predictions. As we mentioned earlier, there are 2 ways to get predictions, batch and real-time. Batch predictions are for asynchronous large volume prediction generation. For example, you may have a Redshift cluster that you update on a daily basis with batches of data, and you want to get predictions for these data records at once. So batch prediction interface is the right match for that, and you'll see this in the demo. You can also obtain real-time predictions at low latency synchronously. An API request comes in, and you get a response immediately. And this interface can be used to obtain predictions at high throughput. This interface is key for applications that deal with one record at a time. Say, for example, you have interactive applications that need to do something for the user like right away. So you need to make a prediction on what content to show that user. Here's an example data flow for batch predictions with Redshift. Here, we have structured data in Redshift. You can query this data directly from Amazon Machine Learning to create a data source and to obtain predictions for this data source using the batch API. These predictions are output to S3. Then you have a choice. You can import these predictions back into Redshift and merge them with the data that is already there, or you can pick them up from S3 and consume them in your application directly. The choice is really yours. It all depends on what makes sense for your application or your use case. So a good example here is, say you have an application that periodically receives new product descriptions and needs to classify them into categories. For example, like assigning genre to movies based on the movie metadata. So now let's see how you can visualize your predictions with Amazon QuickSight. So Amazon QuickSight aims to simplify the process of deriving actionable insights from a wide variety of data sources quickly, easily, and at low cost. QuickSight is designed to work with all the data that you have already stored on AWS. This means that the service is able to look inside your data sources already available in your AWS account. For example, with the right permissions, QuickSight will look at data inside Redshift. QuickSight will take a look at not just the data sources, or rather the sources of that data, but inspect the data types inside that data and look for the relationships between those data types. This allows QuickSight to build up a lot of information and intelligence about the types of data that you're working with. QuickSight then selects the best visualization for your data automatically using a technology called Autograph. Not only does Autograph make recommendations about the types of graphs, but also the types of variables and the data that you want to plot against each other for that visualization analysis. Here's the meta architecture of the product. To access QuickSight, pick your favorite mobile device or web browser, connect through the UI to our core engine. The engine consists of 5 key components. There's a data connector that's built into the product that automatically discovers and connects to all AWS data sources. That means, as a user, you don't have to worry about how to connect with our data sources. In addition, using JDBC and ODBC drivers, you can connect QuickSight directly to your data source on-prem. So we then look through the datasets and build your data catalog using the metadata feature. Once you select your data source, you can start to visualize it immediately, or you can use our data prep feature. Data prep allows you to specify what subsets of data you're interested in. You can write filters to reduce the scope of the dataset. And then once you start interacting with your data, the Spice engine kicks in. It ingests the data and responds to all your queries really fast. Spice is a brand new technology that we have built from the ground up. Spice stands for Super Fast Parallel In-Memory Calculation Engine. What Spice allows you to do is to collect and compress data in a columnar way and optimize it for in-memory use. QuickSight will immediately detect all the data relationships and then tells you the right sets of combinations of visualizations that make sense using the suggestions feature. Our goal is to deliver insights to you easily. We are working with our BI partners to integrate Spice engine so that they can deliver the same experience to their end users. So how do you visualize predictions with QuickSight? Once you generate your predictions using Amazon machine learning, you can load your predictions to Redshift and visualize the predictions directly with QuickSight. If you're using a BI tool that integrates with the Spice engine, Spice can ingest your predictions from Amazon S3, allowing you to visualize them with your BI tool. And with that, let's turn to the demo with Radhika.
Thank you, Mangeshi, and thank you everyone for joining us today. In this segment, we are going to demonstrate building a smart application to predict delays for flights originating in Chicago's O'Hare International Airport using Amazon Redshift and Amazon machine learning services. To give you a bit of background about the problem, every year approximately 20% of the flights are either delayed or canceled, costing travelers billions in time and money. The focus of this demonstration is to analyze massive amounts of data to predict whether or not a flight originating in Chicago is going to be delayed. Before we dive into the demo, let's take a quick overview of the architecture behind this application. For the demo, we have staged FAA flight data as well as climate data in an S3 bucket. We then used Redshift's copy command to copy that raw data set into Amazon Redshift, where we analyze the data further. We then use Amazon machine learning to create and train models based on this data and generate predictions. The predictions themselves are outputted to an S3 bucket, which are later copied to the Redshift cluster, and we use Amazon QuickSight to visualize the prediction accuracy of our models. So with that, let's jump in and take a look at how this all works together. So as Vangashi mentioned, the smart application begins with the creation of a model. In order to create the model, we need a data source. What you're looking at right now is a data source wizard in the Amazon machine learning console where you're presented with a simple question: where is your data located? In this case, we are using Redshift as a source of data. Once we input the mandatory parameters for our cluster, we go to the next step where we look at the schema. Now, before I go into the next step, I quickly wanted to take a detour and explain a couple of things. Now, just because I'm issuing a query against a Redshift cluster, it doesn't mean that we are copying the data into ML, Amazon ML. This is, in fact, just a reference to the data source, which is Redshift in this case. The second thing I wanted to talk about is the query here is very simple, but in order to come up with a data set that actually works for our model, we had to leverage several of the user-defined functions that Wangeshi spoke about. For example, holiday season has an impact on the flight delays. So in order to compute whether a given day of the month falls during a holiday season for that year, we wrote a user-defined function that was used in the creation of this table. So let's go back and go ahead and create a data source object. So the next step in the data source object creation is the schema. Amazon machine learning looks at the first few rows for the data type for your input variables. Here in this screen, you can verify the data type or correct them to meet your expectations. In this example, I am going to make flight num as categorical and even hour and month as categorical. Once we settle down on the schema, we are asked to select a target. A target is a variable that you're trying to predict. It's the name of the attribute in the input data that contains the correct answer. Amazon ML uses the target, which includes the correct answers, to discover patterns and generate the model. So what we are interested in is determining the delay for a flight, which is a binary. So we are going to select the target variable delay as our target attribute. We can optionally add a row identifier. Row identifiers are of great help when you want to understand how the prediction rows that we are going to generate correspond to the observations from your input data. For the purpose of this demonstration, I have created an ID and I'm going to use a ID that I have created for this input data. And we'll see later in the presentation why it matters. Once we have all our input ready, we are ready to kick off a data source object creation. So while the data source is being prepared, let's go ahead and take a look at an already created data source object. Now, the data source object not only allows you to connect to your data source, it also gives you insights into the data that you have inputted. For example, it computes a number of descriptive statistics that will help you learn more about your data. As an example, let's take a look at the target visualization. Now, this chart here is saying how your target attribute is distributed over your data source. I can tell that over 700K of the records are not delayed, or the flights are not delayed, and very few of the flights are in fact delayed in the input data that we have provided. In addition to these, uh, the target visualization, you also can look at other variables and find out how they correlate to your target. For example, if you want to see if the precipitation or snow, how is it impacting your target, you can take a look at this, or even look at a histogram that is being generated for you. The data insights also provide you with missing or invalid values as well as the mean and the median. Once you study your data in depth and are content with the final data source object you have, the next step is the creation of a machine learning model. Let's go ahead and do that. So the first step in creating a machine learning model is to give it the input data that it can train with. So for the purpose of this demonstration, I am going to use a data source that is already ready and going. Once I provide the input data, it automatically surfaces up all the metadata associated with the data source ID. And then the next step is looking at the model setting itself. Now, supports three kinds of models. The first is a binary classification model, which pretty much answers simple questions such as, is this email a spam or not? Is this transaction fraudulent or not? Model that Amazon Machine Learning supports is a multi-class classification, where you ask whether a product belongs to a particular category. And finally, we also support a regression model, where you're asking how many items are going to sell. So because we chose our target to be a binary, machine learning already determined the model type to be a binary classification problem. The next thing that we want to look at is the training and evaluation settings. Machine learning models are only as good as the data that is used to train them. One of the key characteristics of a good data is that it is provided in a way that is optimized for learning and generalization. Amazon Machine Learning automatically determines the optimal transformations that need to be applied on your input data. You can optionally choose to create your own transformation using a simple JSON string and customize your transformations to meet your business needs as well. So once we have our recipes and model settings ready, we go ahead and create this model to train with. Now, while the model takes a few minutes to come up, in the meantime, let us go ahead and take a look at the already created model. One of the first things that you want to do once you create your model is evaluate how it fared. And if you go to the model summary page and click on the summary, you are presented with an evaluation summary for that model. Amazon machine learning provides an industry standard metric and a number of insights to review the predictive accuracy of the model. Because this is a binary classification problem, machine learning uses a metric called area under the curve. The area under the curve metric is used to measure the quality of your ML model and typically ranges between a value of 0.5 and 1. The higher your AUC score, the better your machine learning model quality is. One of the other things that ML does is it also outputs a score that ranges between 0 and 1 for each record that you provide. The higher the score, the more likely that your observation is a positive one, meaning a 1. You can interpret the score by picking a score threshold that is shown here. Now let's dig into this score threshold a little more. When we click on that button, Amazon Machine Learning presents us with a chart that explains how our model performed. Now this is a binary classification model in which there are bound to be some errors. The errors typically fall into two types, false positive or false negative. Now, if you're considering flight delays, a false positive refers to flights that are not delayed but reported as delayed. A false negative errors apply to flights that are delayed but are not reported as delayed. Now, as you can tell, you want to minimize the cost of a false positive is higher here because the flight is not delayed but yet reported as delayed, and I might end up missing my flight. So machine learning allows you to minimize the false positive in your input data by simply adjusting the slider to see how much errors you can tolerate. Now, once you're satisfied with your model performance, the next step involved is creation of the predictions themselves. So let's go ahead and we have gone through the steps of creating a data source object. We have created our ML model. Now it's time to create some real predictions. To create a model, to create a prediction, the first input that the machine learning service needs is a model. So let's go ahead and click on select a model. The second variable that it needs, the input that it needs, is the test data to work with. Now, when I created the model in the earlier step, I have provided the input data for flights between the years 2005 and 2007. And when I want to make predictions, I want to make predictions for the year 2008. So let's go ahead and select a prediction data source object that I have already created. So Amazon Machine Learning validates your data source, and once it's ready to go, we have one more step, which is specifying where my predictions should be outputted to. In this case, I'm going to select a bucket that I have already created for the output. And with that, we click on Finish, and the prediction should be ready in just a few minutes. So in the interest of time, I am going to go into my S3 bucket, where I already created a batch prediction for the same model and the data set that we just went through. So once your batch predictions are ready, a folder called batch prediction is created in the bucket, and that folder essentially consists of a manifest file and a results folder. The manifest file has information that maps your input files to the prediction output files. And the result folder consists of the actual prediction results. They are gzipped and ready to go. Now, wouldn't it be cool if we can unzip one and take a peek at how a prediction file looks? Well, I have already done that. So let's take a look. Columns. The first one is called a tag, the second one is best answer, and the third one is score. Tag refers to the row identifier that we specified in the data source creation stage. Best answer is a prediction label of 1 or 0, which is calculated by evaluating the prediction score against the cutoff threshold that we reviewed in the model performance page. And finally, we have a score column that contains the raw prediction score assigned by a machine learning model for this type of prediction. Now that we have made some predictions for the 2008 flights, we are curious to know how this model performed and compare it against the actual data. To do that, I have uploaded all the prediction files into my Redshift cluster, and once I have the data there, I correlated the predictions with the actual data. And finally, once I put them in a format that I want, I generated the prediction accuracy for my model per hour as well as per carrier. So what I have here on the x-axis is the number of flights during the year 2008 originating in Chicago Airport. On the y-axis, I have the accuracy category. Now the accuracy category I determined has four different classes. One is true positive, true negative, false positive, and false negative. So what I'm trying to show here is the model accuracy per hour for the flights originating in Chicago. Now, for each hour, I can tell how many of the flights were truly delayed, how many of the flights were falsely reported as delayed, and so on. And I can do the same thing with the carrier. I used to predict the accuracy of this per carrier for the same flights. Now you can add other dimensions and make other accuracy charts for yourself. So that pretty much is the end of this demo. I strongly urge you to go make your own smart applications. We'll be happy to take any questions from here.
Okay, so we'll take a few questions. There's one question that comes in, and it's, are there any UDFs for Pig Latin? So right now UDFs are supported in Python 2.7. Radhika, will you take another question?
Sure.
So there's also another question that came in, and you want to, a link to the blog that we're referring to. So those links are at the end of the demo. I mean, at the end of the webinar. So once we're done with the QA, we'll go back to this to the slides, and there's a link. There's a slide there that shows all the links that we referred to in the webinar. So there's another question here that says, what's the best way to connect to a particular schema in Redshift? Radhika, will you answer that question?
I apologize, I'm not able to see the questions.
So the question is, the best way to connect to a particular schema in Redshift.
Particular schema in Redshift.
So when you create a data source from machine learning, is there a specific way you can connect to a specific table? So the way to do that is you can create a query. You can create a query, and then that specific query can be geared to a specific table. So as you saw Radhika doing in the demo, you essentially create a query and it can pull all the data from that table based on that specific query. So there's a question here, what about Scala? So if you ask that question about Scala, could you please elaborate? It's not clear what the question is. And then there's also a question on any word on timing for invites to QuickSight. So my understanding is that we may start onboarding customers soon. We just want to make sure the product is ready for you. There's also a question here, will the slides be available for download? Yes, after the webinar, Bowen will go ahead and create, we'll prepare the slides and provide you with a link where you can download them. So there's a question about QuickSight UI. Can that be used directly in lieu of Tableau? So if you integrate, so the way this is going to work is Spice Engine is going to integrate with Tableau, and then you can visualize data from QuickSight or the Spice Engine through Tableau. So if you want to use the UI for QuickSight, then you'd have to use QuickSight directly. So there's a question here, does Amazon provide student accounts to play with this technology? So in terms of Amazon, there's actually a free tier. We have a team that supports local government and academic institutions. So we can take this offline and provide you with additional information on how that's related to students. Let's see if there are other questions coming in. There's also another question about PDFs of the slides. And again, at the end of the webinar, we will send you a link where you can download the slides. There's also another question. Is there a walkthrough tutorial of this presentation? So currently we don't have the walkthrough tutorial, but we plan to prepare a tutorial in the coming weeks, and we will let you know. There's also a question. Okay.
Sorry, Vangeshi, I'm going to take the questions. I apologize. I had some technical difficulty here. So other example data sets that can be used for learning. So there are plenty of publicly available data sets. There are several websites that host this kind of data. We ourselves have downloaded the data from FAA and National Oceanic and Atmospheric Administration's website. You can go to the same ones and get your data for machine learning.
So there's also another question that just came in. Are there plans to integrate R closer to Redshift as vertical, for instance? So here at Amazon, we are basically customer driven. So we'd love to hear what your use case is. So you can share with that offline, because our roadmap pretty much depends on what customers are telling us. So we'd love to hear about your use case. So there's also a question here. When loading data, can you do transformations, joining fields, and so on? So as you saw, when you create a data source to Redshift, your query can be as complicated or as complex as possible, because the idea here is you want to grab a data set that makes sense for your use case, to create that model and train it and then generate predictions. So Radhika, do you have other questions?
Yeah, I'm looking through them. Is AWS partnered with MicroStrategy? Yes, MicroStrategy is one of our partners. I don't see any other questions.
Okay, so it looks like the questions are over.